This lesson is on domain and range of a function. Let's do a recap. We're going to find the domain and range of this function. Now we know this is a quadratic function and its shape is a parabola, so there are some restrictions on the domain and range. You must be able to sketch the graph of y equals x squared quickly and correctly from memory. So you need to be able to graph the basic parabola. Know the coordinates. This will make transformations easier. So here are the coordinates, 0, 0, 1, 1, 2, 4, 3, 9. Of course, every y value is the square of the x value. You sub in a 3 into this basic function here. You sub in a 3, you get out a 9. You sub in a -2, you get out a 4. So these are your coordinates from what we call the parent function. It's the function that has no transformations of the quadratic. So we want to graph this one, and it's helpful to know how to get this one pretty quickly. The first thing I know about this function here is its vertex. So its vertex comes from what makes this bracket equal to 0. So that would be the 2. And this number here is a 3. So the vertex of this one is going to be 2, 3. So 2, 3, and this a value is a 3. A value equals 3. That means it's going to open up and it's going to be stretched. So I'm going to place my axes kind of low. If you look at the graph on the right here that was already done for us, the x-axis is low because the vertex is low and it opens up. So we don't need a lot of space down here. So when we have graphs, we don't need to waste paper. So I'm going to put my x-axis low as well, and my y-axis through the middle. And remember, I must label a scale on here. I'm going to count by ones, but I'm going to label every second one so I don't get too crowded. And I also have to label my axes. Usually it's x and y, but sometimes that's a t there for time, or an h for height up here. So we need to label our axes with the appropriate variables, whatever variables are in the question. Here's a y, here's an x. So I know that I have to use x and y. So press pause here and continue to label your scale. All right, so press pause if you didn't yet, because there's my scale all labeled. Now I'm going to put my vertex on, which is 2, 3. So I'm going to put a dot right there for 2, 3. And then comes the hard part. The vertex is step 1. That's the easiest part to place. But then I have to figure out the a value, how to get the rest of my parabola. So let me put my vertex on at 2, 3 right there. Now let's look over at the parent graph. From the vertex on the original graph, we would normally go over 1 and up 1. Let me write that over here. We would normally, from the vertex, go over 1, and then we would go up 1. Up 1. Okay, but we're not going to go, this is the part that changes. So we're still going over 1 from our vertex. Our vertex is down here, right? We're still going to go over 1, but I'm not going to go up 1. What I do is I take my a value, which is a 3, I multiply it by that number 1 times 3. So what I'm really going to do is I'm going to go up 3. So instead of over 1 and up 1 from my vertex, I'm going to go over 1 to over 1 and then up 3. 1, 2, 3, and there's a dot. So that's how I get my next coordinate. And I need 5 would be good. If I could get 5 points on here, I don't know if I'll be able to fit 5. But I'm going to get 3 for sure. So now I'm going to go in the other direction. I'm going to go over 1 to the left. And again, I'm going to go up 3. 1, 2, 3. Now, however you learned to graph in grade 10 is the way you should continue to graph your quadratics, because that's not going to change. You can continue to use a step pattern or whatever you've used in the past. Okay, let's look for our next coordinate. So back to our basic graph here. Let's look at our vertex at 0, 0. The next point I want to look at is 2, 4. So that means from the vertex, I went over 2. To get to that next point, I went over 2. And then I went up 4. But this part is going to change. Instead of up 4, I multiply it by my a value, which is a 3, and I'm really going to go up 12. So I probably can't fit that in. Back to my graph, looking at the vertex, I'm going over 2 and then up 12. So I don't think I'll be able to fit it in, but I'll still put it on here. There's up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can almost fit it. 11, 12. We'll put another one about there. Now that coordinate is not, I don't want you thinking, oh, that coordinate, we went over 2 and up 12. The coordinate's 212. Sorry, 212. No, it's not. That is not 212. That's just how I counted out my transformations. 212. The coordinate is not 212. But what is the coordinate? So look at what your coordinate is. Let me change colors. I'm down 4. My x value is clearly a 4. So my x value there will be a 4. My y value, so I went a little higher than my grid. I don't actually have any grid lines there. But I was at a height of 3. My vertex was already 3 units up here, and then I went up another 12. So 415 would be that point. So that's what that point would be. It's off my grid. If I'd made a better scale, or if I'd moved my x-axis lower, or if I had a big piece of graph paper like you might have when you do your homework, then you could fit a few more points on it. It's usually good to get 5 if you can. So I'm going to put my other one symmetrically opposite that one, which would be at 0, 15. And now I can draw a curve connecting those points, but I'm going to erase all these little marks first. There we go. My vertex was at 2, 3. And then I've got a few other points on there. And you can see, comparing it to the pre-made one I have on the top right, it's vertically stretched. So this green one here is a vertical stretch from the basic one by a factor of 3. So we took all of our y's and we pulled them up. So all of these y values here, they would all get multiplied by 3. And so everything went up to be stretched by 3. Again, you have another way of graphing that from grade 10, then just stick with that. You don't have to graph it this way. You can graph it however you learned how to graph it. Now we didn't need to graph it to actually answer the question, which is find the domain and range, but it's good review to graph it. So how do we find the domain and range? Well, now we have a graph. It's pretty easy to look at the graph and see. Domain, remember domain, we open up a curly bracket here. Domain, those are our x values. So we start with our number system. X is an element of real numbers, meaning positives, negatives, decimals, fractions, all those rationals, irrationals, everything. So we can sub in any number we like right here up at the top into our equation. Any number I like, I could sub in for x. Any real number I like. There's no restriction. I can't say, oh well, once I get to x equals 20, then I can't go any further. That's not the case. So for all quadratics, unless they're a word problem, all quadratics are x is an element of real numbers. That's the domain. There's no restrictions on your x's. You can put whatever you want in there. But what about the range? So there is always a restriction on the range. We start off first by identifying that we are using real numbers again. Remember, this straight vertical line means such that, make it more straight than that. So y is an element of real numbers such that. So we have a bit of an exception here. Look at the y. This is my y-axis here. Look at all these y numbers. When y is 6, yes, we have our parabola exists there. When y is 10, yes, absolutely, our parabola is there. When y is 12, when y is 100, when y is 1,000,000. These arrows are important here because they're telling me this goes up to infinity, and this is helping me with my range. These arrows telling me that this graph keeps going. These y values, when they get huge, like 1,000,000, the graph is still there. But what about these y values down here? At -1, there's no graph here. There's nothing here. So we have a restriction on our range, and we always do for quadratics, and it's based on the y value of your vertex. So this number right here. So you don't have to graph it to see this. You look at this number right here, and you see that it's opening up. So my range is going to be y is an element of real numbers such that all of the y values that will be used by this graph, they're all greater than and equal to 3. So that's the domain and range of this quadratic. Continuing on, example 1, we're going to write the domain and range in set notation for this. So this is not recap. Our last example is a recap, right? This is new. We have never done this before. This radical sign or this square root sign. Brand new function. This f at x, you will see this because we're in section 1.4, and the way I teach the course is I start with 1.1 and then I kind of jump to 1.4, then I go back to 1.2. So this is showing up in your textbook probably. When you see this, you can just, if you want to, replace it with a y. I'm gonna explain that notation later. So y equals. Now we have never done anything like this before. So this function, it's not linear, it's not quadratic, it's a square root or radical function. So this is new. And the domains of them are restricted and the ranges are restricted. So we'll get to these points here in a minute or two. I just want to go over the function. So to find the domain and range, we're going to create a table of values and use it to sketch a graph. This is the best way to determine domain and range if you're unsure of the functions. Even with the quadratic, the parabola that we just did, I did a sketch of it just to be sure of the range, right? To be sure of that. But once you have a good understanding of quadratics, you don't need to graph them all the time to get the domain and range. You should know from the vertex and the direction of the opening. But this is new. So we're going to start with a table of values here. So I have f at x there, but we're going to just say y. So y equals, and our equation goes there. That's what we're trying to find out. Now, I want some values for x. So this is harder because I can't just pick any value for x like I used to be able to, because I've got this really tricky operation to do here. What's most important whenever you have an equation with a radical sign in it or a square root sign in it is finding what we'll call its vertex. Just like the quadratic, the vertex is really important. We find the vertex when it exists where just the radical part, this part here, I want that to be a 0 underneath there. So what does x need to be? So what's the value of x so that the square root of 1 minus x will be equal to 0? So I want this part underneath 1 minus x to equal 0. What's that going to be? Well, I can just solve this. I maybe do it in my head, or I solve it. I can bring the x over this side and I get 1 equals x. So when x is 1, I'm going to get a 0 under there. So let's look at what I put in the box here again. Let's just put a 1 right there. 1 minus 1 is 0, and that's what I want to find. So let me erase that. So that's our first x value that we're going to start with. We're going to start with the x value of 1. So when x is 1, so I'm going to ignore this, right? I'm just going to think of it as y for now. My y value, when my x is 1, is going to equal the square root of 1 minus 1 plus 4. So that, of course, 1 minus 1 is 0. That's going to be 0 plus 4, which is 4. So we have a coordinate here, 1, 4. So that's a really important one. That's going to be our vertex. Now we need some more. Now I can't just put in whatever number I want here, right? Let's say I put in a 2. If I put a 2 in here, I'm going to get y equals the square root of 1 minus 2 plus 4. Now the square root of 1 minus 2 is negative 1, so I can't do that one. Remember we talked about numbers that we can and can't sub in, so I can't use that. That's not going to be in my domain. I'm not going to be able to use 2. So am I going to be able to use 3? Would I be able to use 3? That would be 1 minus 3. No, I can't use 3 either. So you need to see a pattern here. And the pattern is always, even if I go just ahead, I already know 1 works, so let's just try 1.1. If I try 1.1, I'm going to get y equals the square root of 1 minus 1.1 plus 4. No, that's going to give me negative 0.1 plus 4. So I can't use that. That's important at finding the vertex, because once you find the vertex, you're only going to be able to use x values on the right or the left of the vertex. So I can't use any of these numbers. Let me erase just to make some room. I won't erase everything, but I can't use any numbers that are bigger than 1, because as soon as I put in a number that's bigger than 1, like 1.1, I can't get an answer. So let's go on the other side of 1 and look at numbers. Let's try 0 on the other side of 1. Sub in a 0. Let's see if we can do anything with that. Y equals square root of 1 minus 0 plus 4. Yep, that's the square root of 1, which is just 1. 1 plus 4, that's a 5. So I have a coordinate here, 0, 5. I'm not going to be able to, so I'm going to graph this later, but when I graph it, 1, 2, 3, and I'll erase this in a minute. I'm not actually going to graph it here. I've got a vertex at 1, 4. Let's see, that's there, 1, 4. But my graph will not exist anywhere over here. My graph's not going to exist there. So there's no sense looking at any of those numbers. I figured that out now by subbing in the 2. The 2 didn't work. Okay, so I can only sub in numbers to the left of 1. And that's not always going to be the case, but it is for this one. So let's get another number here. What about negative 1? We sub in a negative 1. We get y equals 1 minus negative 1 plus 4. That's really 1 plus 1. So the square root of 2 plus 4. But square root of 2 doesn't work out evenly. And I don't really want to graph any decimals here. So I don't want to use negative 1. So now I want you to think, and you might need to press pause to think. I want you to think of an x value I can put in here that when I sub it into this equation, 1 minus x, I'm actually going to get a number I can find the square root of. Like I can find the square root of 16, or I can find the square root of 9, I can find the square root of 25, I can find the square root of 4. So try to think of numbers for x that we could use that will give us these so that they're easier to sub in. So I want you to press pause and think about that. Okay, did you come up with negative 3? Negative 3, that gives us 1 minus negative 3 plus 4. That is what equals there, sorry. Y equals 1 minus the 2 negatives make it positive. There's my 4. 4 plus 4. So the square root of 4 is 2. That gives me 2 plus 4. So I have a coordinate here, negative 3 and 6. So that's nice. Can you think of another one? So we got this one. Right? We got this one. And we already got the square root of 1, and we already got the square root of 0 in our earlier ones. They're done. So it'd be nice if we could find one more. How about the square root of 9? What number do I need to sub in for x so that I can get the square root of 9? Hopefully you already figured that one out. 9, so that's negative 8. We sub it in negative 8, and we get this. I had to crowd it in down there, sorry. We sub it in negative 8, and we get a 7. So we have some coordinates we can graph here on our brand new radical function. Again, the question did not ask us to graph it, right? It says find the domain and range, but as I suggested here, it's pretty hard to do that when you really can't even picture this. You don't even know what it looks like. Let's look here. The domains of a square root function are restricted because the square root of a negative number is not a real number. So these answers that I was getting here, I'm not allowed, I can't use those. So my domain, remember x is domain, so when I get to my writing out my domain, I see here from these values that it's not just x is an element of real numbers. It is real numbers, but not all of the real numbers. Let's just put a sketch down to get a little more of an idea of what we've got here. So I got to put an x and y axis in here. So as I was just drawing my axes in there, I looked at my coordinates that I got and I saw that all my y values are positive. So I can put the x-axis down kind of low here. So there's my x-axis kind of low. And then I know my y-axis can be over a little bit to the right because the only positive y value I have is 1. So let's get our numbers on here. Another thing I wanted to point out, I'm not sure if I did or not, if I'm counting by ones here on the right, I can't now count by fives or something, -5, -10, right? I have to use the same intervals. So I can't change that. But what I can do is I can change my y. I don't have to count by ones on my y-axis. I can change the y-axis. They could count by 10s if I wanted to, but then it has to be 10s all the way from up and down on top and bottom of the y-axis scale. But I'm going to count by ones everywhere. All right, we've got our axes done. Let's get our vertex on there. 1, 4. There's my vertex. It's just on the edge because I don't need the numbers. I don't need more numbers on further to the right from that. So I just put my axes there. Now 0, 5 and -3, 6 and -8, 7. This question, the original question we were given right up at the top, there was no plus or minus. If you look at the top, I'm just going to put it in. See the plus or minus I'm putting in here? That wasn't there. If it were there, for example, plus or minus the square root of 9, well, that means the answer is 3 and -3. If you don't have that plus or minus, then it's just the positive square root that you're looking for. Just the positive, you're not looking for the negative square root. So I just wanted to point that out. I don't think they do that in your homework anyway. Now I could have got more numbers here. So which way is my arrow going to go? I've got 4 dots on the graph. How do I know, because I've never graphed this before, how do I know where it actually goes? I don't just want to connect my 4 dots because I know that's wrong. I know that I could have subbed in more x values. I just stopped. I literally ran out of room. I just stopped. So could I have added more on this side? Is there going to be an arrow here? Could I have kept going this way? No, I couldn't. Remember, we tried to get 2 and we couldn't. We couldn't use 2. So this is a vertex. And then my graph is going to come around here, and here's where I could keep going. I could have an arrow on this end because I could have kept subbing in more numbers here on to infinity. I could have kept, this will go on to infinity here, but only on that one end. So I'm going to connect my, come from the top here, connect my points. That's not very smooth. Connect my points here and extend it out like that. That's what the radical looks like. The radical has a vertex. Let me label the vertex. That's 1, 4 is the vertex. And then it's like you've turned your page sideways and you've drawn one leg of a parabola. That really is what it is. And we're going to talk about that later. That's technically what it is. We've only drawn one leg or one arm or one side of the parabola here. So it has a vertex like the parabola does. And we find the vertex by looking for the square root of 0. Just like in the vertex, if I had x minus 2 squared plus 1, I want to know what makes this 0. That gives me the vertex, so it's the same idea. So there is our radical, and now we can finally look at the domain and range. Again, we didn't have to draw the graph to get that, but it's very helpful when you've never drawn anything like that before. So domain first. The domains, we already talked about this. They're real numbers, but we can only use some of them. We are restricted. So I'm going to write my domain here. Capital D first, domain, colon, curly brackets. So my independent variable is an x. X is an element of real numbers, so I could have subbed in decimals, fractions, whatever I wanted. I just didn't because it would have made my graphing really difficult. So I chose specific x values, but I could have picked whatever I wanted. x is an element of real numbers such that, so we have a restriction here. We haven't had a restricted domain yet in the course. The only x values we can pick, we realized, have to be less than or equal to 1. All the x's we can use 1, and everything else was less than or equal to 1. So we have a restricted domain. We tried 2, didn't work. We tried 3, didn't work. We tried 1.1, that didn't work. So we're only using values that are less than 1 for this one. And how about the range? So the range also, if we look at the last little rectangle in this chart here, the ranges are restricted because the square root sign refers to positive square root. So that means we're not getting, we can't get multiple answers out of here. We don't have a plus or minus. That's only part of the answer here. But when I look at the range, this is only going to increase. So again, it's like a parabola. It's just going to keep going in this direction. It's not going to curve around and come down. So my lowest value for my range is this number, much like what it was for the quadratic. So 4 is my low number here. And then all of my y values are all higher than 4. Now it is possible, in other cases we will do this, where we're actually drawing this side right here. If we were drawing this side, then it would be the y values less than 4. But we're going higher, the one we did, so we've got greater than 4. So my range is y is an element of real numbers, meaning I'm going to get decimals, fractions, all kinds of y values. But all of the y values that we are allowed to use have to be all greater than or equal to 4. So the two numbers that you see here in the domain and range, the 1 and the 4, they come from our vertex. So that's why it's really important that you find the vertex of a square root or a radical function. When linear and quadratic functions model real-world situations, word problems, then we have even more restrictions with our domain and range. We have to exclude certain numbers. So let's see what I'm talking about here. A submarine at sea level, so this is sea level, descends 50 meters every 5 minutes. First thing we want to do is just get an equation of the function that models the situation. This is linear, 50 meters every 5 minutes. So this is linear. Put an answer, I'll put my work down here. So it's going to be linear. And that is y equals mx plus b. So how do we get values for this? Well, actually, let's change our x and y to variables that make a little more sense for the question. What is our independent variable? So instead of x, what is our independent variable? That's going to be minutes, so time. So I'm going to change my x to a t, and my dependent is the distance or the depth. So let's say the depth is equal to mt plus b. I'll put that up here. Let t represent, because I'm changing from x and y, so let t represent time. And if you don't know what ditto marks are, I'm putting them right here. That means repeat what's above. You guys probably use this for that maybe, but ditto marks are better. So let t represent time, and we're not going to use the word time again. Let t represent time and let d represent depth. So there's our let statement. Now we need to find m. M is the rate of descent in meters per minute. So our m is equal to, so our rate of descent meters per minute is 50 meters, but it's a negative because we're descending, right? So 50 meters for 5 minutes. That's what was in the question, so I'm just going to reduce that. So my m is equal to -10. So if we're descending 50 meters every 5 minutes, then that means we're descending 10 meters every minute, per minute. So we can put a value in for M. And what about B? B is our y-intercept. Y-intercept or initial value. Initial value. So where are we starting? Where is this submarine starting here? So it's starting at sea level, and sea level has a depth of 0, right? Sea level. So our equation is D equals negative 10t plus, now you can put a 0 here, I'm just going to kind of make an invisible 0. We don't really need that 0 there. You can put it there if you want to, but the y-intercept is 0. So there's our answer for part A. Part B says, if the ocean floor is 3 kilometers beneath the surface of the water, how long will it take the submarine to reach the ocean floor? We have a new number. Anytime we have a new number, it means we're going to be subbing it in somewhere. Problem is, this is kilometers, and we made our equation in meters. So 3 kilometers is how many meters? 3 kilometers. So 1 kilometer, remember, is equal to 1,000 meters. So 3 kilometers is 3,000 meters. And it's descending. It's gone down 3 kilometers, so it's actually a negative. Well, let's sub that into the equation. Our equation was, so I'll do part B right here. Our equation was D equals negative 10t. And we have a value for D, negative 3,000 equals negative 10t. Divide both sides by negative 10 to isolate t. And we have a t over here, and this is a 300. So 300 minutes. Of course, we would never say 300 minutes. We would convert that to hours. So, how long will it take to reach the ocean floor? Therefore, it will take, so what is 300 minutes in hours? 300 divided by 60, because there's 60 minutes in an hour. It will take 5 hours. 5 hours for it to get to the ocean floor, assuming a linear descent, which is what we are assuming. Part C, no. So part A and B, we could have done that in grade 9. But part C, we're going to talk about domain and range. What are some values for the domain and range that wouldn't make sense, and in this case will be excluded? State the domain and range of the function in this situation. So this is what this statement is about here. When we have real world situations, word problems, we often have to adjust our domain and range. So let's talk first about the domain. Domain. And our domain is t, so I'm not going to start with x as an element of real numbers. I'm going to write t. Time is an element of real numbers. So by real numbers also, you need to think about, so real numbers means all decimals, all fractions. So between the numbers 1 and the numbers 2 are an infinite amount of numbers, not just 1.1, 1.2, there's 1.001, there's 1.00001. There's lots of numbers, and time is continuous. So our time doesn't start at 1 minute and then jumps directly to 2 minutes. We've got all those seconds in between. So when we say real numbers, we mean every little fractional piece of a number in between our whole numbers. That's what we mean by real numbers. So time is real numbers, continuous, right? It doesn't jump from minute to minute. And what are the numbers for this question? Well, we know if we're talking about this situation, the question says this situation, so getting to the bottom of the ocean, so we know 300 minutes is how long it took for this particular problem, 300 minutes. So 300 is our high number, our maximum number. But we have a low number too, because time can't be negative. So our time has to be greater than 0. So we always write and when we have a low number and a high number, we put the low number here and we put the high number here. So my low number is 0, That's less than or equal to t. So that's when it was at in the picture, when it's just sitting at sea level. And then to get to the bottom, the high number was 300. That's the most amount of time. So that's our domain. Now the range, we didn't use y this time, we used d for depth. Depth also is an element of real numbers. The submarine's not going to jump from 1 meter directly to 2 meters below the water, below the sea level. It's going to pass through every portion of distance between 1 meter and 2 meters. So depth is an element of real numbers. We also have restrictions. What's the low number here? Well, the low number, we were given it in the question, the low number, we got to stick with the same units, is negative 3,000 meters. That's the low number, so that's less than or equal to all the d values. And then what's the maximum d value? Well, it's 0. That's sea level, because we're assuming this submarine isn't going to shoot up above the water like some kind of movie. That would be our maximum depth, our maximum height of the submarine would be 0 meters. So that is the domain and range, and we excluded all the values that did not make sense. Example 3 is our last example. State the domain and range of this relation and whether the relation is a function. This is a real weird one. Look at this picture here. It doesn't look like a parabola or even the square root one that we drew. It looks like a line, but it's even more different than that. But this is called a step function. You can see it being a step, step, step. We've got two pieces of a step function here. Now, one thing you might have learned in elementary school but have forgotten, when you're drawing number lines, if you had an open circle at the end of a number line, it means you're going right up to that number. So in this case, it's a -5. So coming along this line, a -1, -2, -3, -4, -4.5, -4.9, -4.9999, but not -5. An open circle means you are excluding that value. So you need to write that down. If you have an open circle on a line or a function, it means that actual number is excluded. Over here we have a closed circle. So that means for this piece of the step, number 5 is part of this line. The 5 is part of this line. But down here, on this part of the step, number 5 is not part of this line. So this line goes 1, 2, 3, 4, 4.1, 4.5, 4.9, 4.999, and 5, right? It includes 5. Then we jump down here. 5 is not part of this step, but 5.0001 is part of this step. So open circle means you're excluding the value. Closed circle means you're including the value. The domain or range of this step function, so you should write that down too, it's called a step function. The domain or range of this step function here. Let's start with the domain. Domain. So those are the x values, remember? So we're starting with the x values. So I'm going to start with x as an element of real numbers. And I'm starting with that because if I look at the x values here, even if I just look at the x values in this piece right here, between 0 and 1, we've got 0, we've got 0 in there, we've got 0.1, 0.2. It's a solid line. So the solid line means all of the numbers between 0 and 1 are all part of the question. All the decimals, all the fractions, all little bits. So that's why we're saying real numbers there. So x is an element of real numbers. So we're using the real numbers, but that's your line, right? But the only numbers we're using, remember we go low to high when we have endpoints on either side. I put my letter in the middle, x. So the low number is a -5. The high number is on the right. So don't think bottom to top. Think the smallest number to the biggest number. -5 to +5. But look at my inequality symbols there. I'm including this one. I'm including that, so I'm going to put the equal to sign there, showing I'm equal to, it always is equal to 5, but this one's not included. So I'm just going to leave that as the less than symbol. I'm not going to make it less than or equal to, because it is not equal to -5. We're going around -5. So there's our domain. Whoops, sorry, I'm not done. Shouldn't put the bracket there. Just had to erase that. Sorry. So now we're going to go over and look at this piece here. So this step is part of our function, and these numbers are part of our domain. Erase this mess I put in here. So the second step also has parts in our domain. And what are they? I'm going to add them on. So I'm just going to put a comma here for now. I'm going to fix this in a second. I'm putting a comma. So let's talk about the domain for this piece. Okay, the domain for this piece, the low number is a positive 5. That's a positive 5. And that's less than, not less than or equal to, because I'm not including it, that's less than x. And that is less than or equal to, what is that, 12 maybe? That's weird. It looks like looks like we're counting by 2.5s, doesn't it? So let's just call that 12. Okay, so those are the two steps there, the two pieces, the two steps. But when I look at my domain overall, instead of looking at it in two pieces, I want to look at it together as one. I can put them together because this is the same number here. I've got a 5 at both ends. So what I'm going to write, a more condensed way of writing this, is x is an element of real numbers such that -5 is less than x. That's this one right here. And then it goes all the way. So I'm using this -5, and I'm using all the numbers right up to this whatever that is, 12, less than or equal to 12. So we put them all together in one domain instead of in two pieces. So I'm going to erase all that because now we're going to move on to range. Okay, the range are the y values. The y values that are in the range. Now take a look at this. There's hardly any. Because these are horizontal, these steps are flat lines, they're only using, like this step right here. Let me put it in blue. Let me just put this dot right here, that one there, its coordinate is 5, 6. Okay. This one right here, that coordinate right there is 2.5, 6. This coordinate right here, right on the y-axis, it is 0, 6. The y's are all 6. That's the only number in the range for this whole piece. The only number in the range for that whole piece is a 6. There's no other y values. So for my range, I'm not even going to put y as an element of real numbers. Well, I'll write it, but I'll erase it just to show you. I'm not even going to put that because it's not real. It's only two numbers. The first step only has the y value of 6. The second step, what's the y value there? It's a little hard. I'm going to say that's a 2 right there. So let's just say that's a y value of 2. Second step just has a y value of 2. So that's our total range. All I'm going to write in here for the range are those two numbers. Anytime you just have a few numbers, you just list them low to high. So our range has just the y values. You can put a y here. You don't have to because you've already put an r there, but the y values are, that's all you need to put, 2 and 6. That's it. And again, you don't need this there. I'm just putting it there because we're just learning domain and range, and I want to point out that the y is the range. So that is it for the range for that question. The only other thing we have to look at in the instructions, always check those instructions. So we did the domain, we did the range, whether or not the relation is a function. The definition for a function is every x value has one and only one y value. And visually we can see that by looking at the vertical line test. So is there any place where I could draw a vertical line would cross twice. So right here, no, whoops, that's not vertical, it's supposed to be vertical. Crosses once there, my vertical line, crosses once there, the crosses once here. The only place maybe is right here. Whoops, let's say that's straight. There's a vertical line. Does it cross twice? Technically, no, it doesn't. It crosses here, yes, but it does not cross here because this is an open circle. Remember that open circle there? So my vertical line, when x equals 5, my vertical line is only hitting the function once, and that is when we had that value of 5 and 6. It is not, I made a big mess, let me erase that. So it is not crossing again at 5 and I think we said that was 2. Right? It's not crossing there because of the open circle. So is the relation a function? Yes. This is a step function. So not a step relation. This is a step function. And the last thing I have here, what I'm just going to read to you, remember that for scatter plots, simply list the numbers like I did here and like we did in our previous lesson. We just list the numbers for domain and range when you have scatter plots if there's no lines connecting them. When the graph is a solid line, so for our domain here, we had solid lines, so we used inequality symbols. But if it's not a solid line, if it's just dots in a scatter plot, then you'll just list the numbers like this. And that's the end of your very important lesson on domain and range.